students, I hope you are fine and enjoying the sessions. Today I am going to start work, energy and power. This is a very conceptual chapter and will be used throughout all the topics of physics. So without delaying, let us start.
Work, energy and power. First of all, I'll introduce you what is kinetic energy. In physics, a moving particle is said to have more energy than an identical particle which is at rest. If we write quantitatively, the energy of the moving particle which is over and above its energy at rest is defined as, mathematically we can define kinetic energy as half mv square. And if we write it vectorially, because velocity is a vector term, so it can be written as half mv dot v. This is the quantity of kinetic energy. It is the energy. This is not an absolute term. This is energy when compared to energy of particle which is at rest. Now as you can see, kinetic energy depends only on the speed, not on velocity. And we all know that to change the velocity, force is required. But force can change its magnitude, its direction or both. Here what we are concerned with is only speed. So what kind of force will be there which is responsible for change in kinetic energy? Of course, the tangential force which is in direction of velocity, because that can only change the speed, not the direction. So from here we can now say that only tangential force can change kinetic energy of the particle. If a force is perpendicular to the velocity, that is the normal kind of force, it cannot change kinetic energy, though it will change direction of velocity, but its kinetic energy will not change. Now from the definition of this kinetic energy I have just stated, we can write that dk by dt is, I am differentiating kinetic energy with respect to time, it can be written as d by dt of half mv square. That can be written as mv dv by dt, and that is equal to, it is m dv by dt, and v is speed here, not velocity, do remember. So it is equal to tangential force with speed, or velocity always has to be tangential, so it is the magnitude of velocity multiplied with tangential force only. Do not write the whole force, because only tangential force is there which can change the speed. But if the force makes angle theta with velocity, so then it can be written as, because ft then will be equal to f cos theta, and then we can write dk by dt as fv cos theta. Now this f is the whole force acting on the body which is making angle theta with its velocity, or it can be written vectorially as f dot v. Now v can be written as dr by dt, so we can write dk by dt as f dot dr by dt as well. And from here we got one very important result, that is dk is equal to f dot dr. If we integrate on both the sides, what is this left hand term? It is change in kinetic energy. Delta k is equal to, can you recognize this term? Integration of f dot dr. Of course, this is work. So it is equal to work. Now here this is work done by the force F, where F is the only force that is acting on the body. So this theorem is called work energy theorem. It is not specified that what kind of force this F will be. So work energy theorem is that change in kinetic energy is equal to work done due to all kinds of forces. Whatever be the kind of force, it can be external, it can be internal, conservative, non-conservative. Later we will see what conservative and non-conservative forces are. But while writing work energy theorem, change in kinetic energy is equal to work done due to all kinds of forces. This is very, very important concept which will be used in almost 50% of numericals from this chapter. So do remember, delta k is equal to work done due to all forces. Now we are seeing that delta K is equal to work done due to all kinds of forces. So how is work calculated? Let us see the calculation of work done. Now there can be a variety of forces for which we have to write separately how work done will be calculated. So first I have taken as the constant force. If the force is constant, what will be the amount of work done? For a constant force, this is the simplest kind of force. So work done directly can be written as F dot dr by definition, and since F is constant, it can be taken outside the integration sign, and then it will be F dot integration of dr, that is equal to F dot delta r. As you can see here, F delta r both are vectors, but work is a scalar term because it is dot product of force and displacement. So work done by a constant force is simply force dot total displacement, or mathematically we can see that it will be numerically equal to force multiplied with displacement in the direction of force. So if force is making angle theta with displacement, it can be written as Fr cos theta as well. This is the work done for constant force. The next is spring force. Now this is the force which is not constant. We know that spring force is given by Kx, where x is extension or compression in the spring. So with application of force, this x will keep on changing. So how do we calculate work done then? Let us write F dot dr. Now if extension is in direction x, I am taking a particular direction, then it can be written as F multiplied with dx. Now one minus sign has to be put here because F we know that is equal to minus kx. So it will be equal to minus kx dx. If we integrate it, because F will keep on changing with time, minus kx dx within the limits when extension is 0 to some extension, let's say x, that will give you minus half kx square. This is work done by spring force. You can see a minus sign is here. What does it indicate? That force is in direction of opposite of displacement. When you are stretching a spring, then force will be in direction so as to restore its original length. So always it will be opposite to the extension or the compression. That's why one minus sign has occurred while writing work done by a spring force. One illustration I have taken for this work done calculation and the kinetic energy that just we have learnt. The first illustration is a particle of mass m is released in a smooth hemispherical bowl from position A. Find work done by gravity as it reaches the lowest point B. Okay, since it has started from here to here and we have to calculate work done by gravity, which is a constant force. So work done has to be equal to, directly it can be written as F dot delta R. That is F multiplied with displacement along the direction of force. Now what is the direction of gravity? It is in vertical direction. So we have to calculate the displacement in vertical direction. As you can see here, from A to B, the displacement is actually in this direction. If you join directly point A with B, that will give you the total displacement, that is delta R. But since it is a dot product here, so it can be written as F is mg multiplied with displacement in direction of mg, which is this displacement. It is equal to R. So directly we can write work done by gravity in this case to be equal to mgr. It's a positive sign here because force of gravity and displacement both are in the same direction, which is vertically downward direction. One more question I have taken here. In this illustration, force is not constant. As you can see here, it is given by F is equal to 3xi plus y square j acting on a body, and body is moving from this point to this point. We have to calculate work done due to the force. Okay, let's start with the initial definition of work done. It has to be equal to F dot dr. Now F is given as 3xi plus y square j. Dot of how dr can be written in xy plane, it should be written as dxi plus dyj. If we take the dot product, it will be 3x dx plus y square dy. Now limits we have to substitute. It is x coordinate initial is 1 to final is 3. Y coordinate initial is 2 and final is 3. As you can see, along z also it has travelled this much of distance, that is equal to 7 meter. But since force is not there in direction of k, so there will be no work for that kind of displacement. Now on integrating, it will come out 3x square by 2 within the limits 1 to 3 plus y cube by 3 within the limits 2 to 3, which is equal to 3 by 2, 9 minus 1 plus 1 by 3, 27 minus 8. That is equal to 55 upon 3 joule. So this is how work done is calculated when force is constant and when it is not constant. One more question I have taken here. A particle of mass 0.5 kg is subjected to a force which varies with distance as shown. Here you can see the force is varying in different manner. First it is along this straight line, and then this is constant from 4 to 8 position, and again this is along a straight line but decreasing with x. We have to calculate work done by the force during displacement from 0 to 4 and 4 to 12. Okay, it is asking for this interval 0 to 4, and then next is from 4 to 12. So let's start calculating for first part. Now from 0 to 4, as you can see, work done will be equal to, because it is graph between f and x, and we know that work done is equal to integration of f dx. Here I have written only dx, not the dr, because f is dependent on x only. So this can be written as integration of f dx. Now if a graph is between f and x and we have to calculate integration of f dx, it has to be area under the curve. So just calculate area under the curve for x is equal to 0 to 4. That will be equal to half into base, which is 4, into height, that is 10. So it will be equal to 20 joule. What about this is our first work. The next work done we have to calculate from x is equal to 4 to 12. Again write this whole area. So its value will be equal to, it's a parallelogram that has area equal to 4 into 10 plus one triangle which has area half into 4 into 10, which is equal to 40 plus 20, that is 60 joule. Which option is correct? 20 joule and 60 joule. This is option number 3. Now come to the second part. The increase in kinetic energy of particle during its displacement from 0 to 12 meter is. Now we know that increase in kinetic energy is equal to the whole work done. So from 0 to 12, the net work done will be equal to W1 plus W2, which is 20 and 60. We had got the values, so it is equal to 80 joule. This is equal to increase in kinetic energy. Which option is this? That is equal to, again, the third option. The third part is, if speed of the particle at x is equal to 0 is 4 meter per second, its speed at x is equal to 8 meter is. Okay, now we have to consider the interval from 0 to 8. So let us write the work done. For 0 to 8, the work done will be equal to, again we have to write the area from 0 to 8, that will be equal to, already we had calculated, so it will be equal to, first is triangle half into 4 into 10 plus the rectangle 4 into 10, which is equal to 60 joule. So this should be change in kinetic energy. Now this can be written as 60 is equal to half mv square. Now what is v square? That is v final square minus v initial square. If we substitute the values now, m is given as 0.5 kg, so it will be 1 by 2 into 1 by 2. Final velocity we have to calculate minus v initial. V initial is given as 4 meter per second. Square of that, which will be 16. Now if you calculate it, it will come out as 240 is equal to Vf square minus 16. So Vf square is equal to 256 and Vf is equal to under root this, that is equal to 16 meter per second. Let's check the options. This is our option number 2. The next illustration, a small object of mass m is moved over a rough curved surface as shown. The force which moves it along the dotted path is always tangential to the curved path. If object moves with negligible speed, find work done by the force. This is the force which is always tangential. In moving it from here, it started and is going to this point B. The coefficient of friction between the object and the curved surface is mu. So we have to calculate work done in moving it from A to B. Now here you can see that this is a variable force. Its direction is changing with displacement because always it is tangential to the force. If we consider the small displacement, because here the direction is continuously changing, so it can be written as dx along horizontal, dy along vertical, the angle being theta, and displacement along the tangent to be ds. Now as the object is moving with negligible speed, so change in kinetic energy should be 0, and if change in kinetic energy is 0, it should be equal to work done due to all the forces. Now what forces are here which are doing work done when this body is moving from A to B? This should be work done by this force, external force F, plus work done by gravity, plus work done by normal, plus work done by friction. Here I have written work done due to all kinds of forces, which is from our work energy theorem. Now if we write all the works, this Wf minus work done by gravity has to be equal to, because work done by gravity has to be nothing to do with the horizontal displacement. So directly it will be equal to minus mg into the vertical displacement, which is y, plus work done by normal always should be 0 because normal is perpendicular to displacement, so dot product will be 0, and work done due to friction. So friction also does the negative work where force and displacement are opposite to each other. So this will be equal to mu n, and along the distance we have to write, so let's write that by s. But do remember that this directly cannot be written as, because this mu n is in different direction, but do remember that this we can write only for the differential small part, because here direction is continuously varying. So every work done I am writing here now in differential form. This will be ds. This whole has to be equal to 0. What is value of n? It has to be equal to mg cos theta, and cos theta can be written as dx upon ds. So if we substitute these values, we can write work done, differential work done by F to be equal to mg dy plus mu mg dx. And on integrating, x is varying from 0 to x, y is varying from 0 to h. So that will give, integrate this part also, so it will give work done due to this external force to be equal to mgh plus mu mg x, which is our desired result. Okay, one more illustration we have. Already we have taken a number of forces. It was constant force, then varying force which was varying with x and y, and then the force which is having always a tangential direction, and the next is a force which is a spring force. A block of mass m is moving, this is the block of mass m, on a smooth horizontal surface with speed v0 towards a vertical wall. A massless spring of stiffness, its stiffness is given K, is attached to the wall such that the block compresses the spring as it moves closer to wall. the natural length of spring being L0. This is given L0. It is asking what is the speed of the block as the spring has been compressed by a distance x. Okay, so again we will use work energy theorem that has to be change in kinetic energy is equal to work done due to all forces. Now as we know, work done due to spring is written as minus half kx square. So from here we can write this to be equal to kinetic energy final minus kinetic energy initial. And that can be written as, if m by 2 is taken as common, v final square minus v initial square. From here we got v final to be equal to, this is v naught square because v initial is given as v naught minus k by m x square. This is the value of speed of block when it has compressed the spring by a distance x. Now for second part, what is the maximum compression produced in the spring? When the spring is maximum compressed, then its speed momentarily comes to 0. So we can write from the starting of motion, change in energy has to be equal to work done due to spring. It is the only force which is doing work done here, which is work done due to spring, because weight and normal are perpendicular to the displacement, so they are not contributing to work. What is this delta k now? Final energy has to be 0 because it has come to a momentarily stop, minus the initial, which is half m v naught square. This has to be equal to work done by spring. Let that maximum compression be equal to x max. So this is minus half k x max square. From here we got this maximum compression to be equal to m v naught square by k to the power 1 by 2. This is the maximum compression the spring will get in the given situation. One more illustration I have. The kinetic energy of a particle moving along a circle of radius r depends on the distance covered s as, this is the variation given for kinetic energy, it is equal to alpha s square. Find the force acting on the particle as a function of s. Okay, so first we have to relate force with the kinetic energy. Now as we know that if k is given as alpha s square, it can be written as half mv square to be equal to alpha s square. Now if we differentiate this kinetic energy with respect to time, we can write mv dv by dt is equal to 2 alpha s ds by dt. Now what is this term m dv by dt? Can it be written as f tangential? Of course it can be. So this is f tangential multiplied with v, which is equal to 2 alpha s. Now ds by dt also can be written as v. So these two v got cancelled. From here we got ft is equal to 2 alpha s. But this is the tangential force, and as it is moving in a circle of radius r, so there must be one centripetal force. And what it would be? That is mv square by r. Now we can substitute value of v square from here, which will give, this is m multiplied with alpha s square into 2 upon r m. These two m got cancelled, and finally we got centripetal force as 2 alpha s square upon r. Now we have both centripetal and tangential force, so then we can write net force to be equal to under root ft square plus fc square. If we substitute these values here, that will come out 2 alpha s can be taken as common, and it will be 1 plus s square upon r square. So this is the value of net force acting on the particle. With this, our today's session is complete. In next session, we will know about potential energy, and before that, some conservative and non-conservative concept I'll introduce. Till then, goodbye.